Okay, take 3. I'm really struggling to get this done this morning. Homework, Nearpod, this week, week 8. First question, centripetal force on car. Centripetal force is mass times centripetal acceleration, as I scroll on the screen during take 1. So that means the centripetal force, so the formula for centripetal acceleration, you will recall, is velocity squared over r. Let's substitute that in for AC. So the centripetal force is, this is going to get messy, is equal to 500 times 6 squared over 10. And I don't remember what the answer was. Times 36 divided by 10. 1,800 newtons. So the next part's a little trickier. The minimum coefficient of friction needed to keep the car traveling along the path. So the car is, traveling around like this. It's traveling at this, it's curving, right? So there's some force keeping it from sliding off the road. And that force is friction. So that force of friction is creating a centripetal force. Anytime you go in circles, you experience a centripetal force, but it's always created by another force. So the force of friction is equal to mu times the normal force. In this case, the normal force and the force of gravity are equal to each other because we're balanced, because we're on a flat road. So that's equal to 1,800. So the coefficient of friction is equal to 1,800 divided by the weight of the car, which is 5,000 newtons. Where did that come from? Mass times G, 500 times 10. All right, let's move on. This next slide was me talking in class about stuff. It's like an introductory slide. I talked about this slide in class. I talked about this slide in class. I talked about this slide in class. And then we had a hoop on a car. This makes no sense whatsoever. I have no idea what a hoop on a car is. It's probably a cut and paste error from one question to another. But we can use the information to do some calculating. The angular displacement of the hoop in radians. Angular speed is 62.83 radians per second. And the time is equal to 3. Reach is an angular speed. So from rest, okay, so that's final displacement. And final speed is that, initial speed is 0. And we want to know the angular displacement. We want to know theta. And so we need an equation that has, basically it's x equals 1/2 v naught plus vf times t, except we're using the angular doppelgangers, so it's 1/2 times 0 is the initial speed, 62.83, and then there's a 3 here. So basically 0.5 times 62.3 times 3, 93.45 radians. We talked about what a radian was in class. And the final tangential speed of the hoop is v is tangential speed, and the tangential guys are always equal to the rotational guys times r. So we take this number and we multiply it by 0.8 to get the answer to that. All right, let's move on. We did this in class as well, starting from rest. So omega naught is equal to 0. We have a mass, we have a radius, and we rotate 95 times 4 seconds. So theta is equal to 95 times 2 pi, right? Because every time it goes around once, it's 2 pi radians, and we need our theta to be in radians. So 95 times 2, 95 times 2, 190 pi. So theta is 190 pi. Calculate the final angular speed of the hoop. So again, we have initial, we have theta, we want final, we have time. So again, we have this deal. It's the same equation we had before. We have right, x equals 1/2 v naught plus vf times t, but now we're using thetas and omegas because it's angular. We're just changing the shape of the symbol because it's angular, but it's the same thing as it was before. So 190 pi equals 1/2 times omega f times 4. So you got to solve for omega f. And I guess we need to do that. 190 times pi. So I always like to multiply the pi out because I'm a physics teacher. And then that would be divided by 2 because 4 times 1/2 is 2. So I get 298 radians per second. And then the tangential speed would be that times 1.1, the radius, that goes here. And then the centripetal force, so I guess we have to do that, times 1.1 is 328 meters per second. Centripetal force, again, is equal to mv squared over r. So it would be 3 times 328 squared divided by 1.1. It's going to be a big number. You know, you could have a centripetal force formula that was in terms of omega if you wanted to skip a step. Let's see if I have a place to write. This has nothing to do with torque, but if centripetal force is equal to mv squared over r, and v is equal to omega r, then this is equal to m. So this would be omega squared r squared over r, and that cancels. So another formula for centripetal force is m omega squared times r. You could use that, and then you wouldn't have to calculate the tangential or v velocity. All right, so then we're going to start talking about torque. We talked about, so this is a lecture slide that I talked about in class, and I do lectures in class. We did this. This question was wrong on the answer key on the Nearpod. So if we have 1 unit of F here at a mark of 2, we need to push up. An upward force to keep it balanced would have to go here, right? Because 2 times 1 is equal to 2, and then 2 times 1 is equal to 2, right? So the product of F and R has to be equal to each other. So 1F times 2R is equal to 2F times 1R. All right, so the answer was B. We talked about that in class, and I admitted how wrong I was, and I brought shame to my family for generations. So then there was a quiz. Okay, I don't know. I guess this is where you showed me your answer. This is a lecture slide. I do lectures in class. And then I had you practice. So this is about where we left off in class. So torque is equal to force times R times the sine of the angle between the force and the lever arm. And if the angle here is 90, then sine of 90 is 1. So for this one, we could just do 125 times 0.3. And remember, the unit is meter Newton, not Newton meter. Here, our force is 330. Our lever arm, we're opening a door here, but we're pushing sideways for some bizarre reason instead of straight. So we would have to do the sine component, right? This component here is going in this direction. This component, not this component, is not doing any torque. So torque is like work in that it's a product of force and a distance, but it's different. In work, the force and the displacement have to be in the same direction. For torque, they have to be perpendicular. So torque is more of a force thing than it is a work thing. Multiple torques. We talked about static equilibrium in class. We did the seesaw problem in class. We did this already. And that wasn't where we left off. I guess this is where we left off. Well, we were definitely doing this in class. I remember this and this are different. So that was silly. So for them to be balanced, the force times the radius of one has to be equal to the force times the radius of the other. Right? So let's just go with 1.5. And so we have 1100 times 1.5. Oops. Oh my God. 1100 times 1.5 is equal to whatever this guy's weight is times 1.9. Anyways, oh my God. $1,100 times 1.5 equals the weight of the other guy times 1.9. And then you solve for the weight of the other guy by dividing both sides by 1.9. All right. Come on, phone. That's been 11 minutes, so we're going to stop this video and start a new one starting on page 25.